Welcome to this problem walkthrough. Today, we'll be solving LeetCode problem number 61, Rotate List. This problem is a great exercise in linked list manipulation and helps deepen your understanding of data structures. Let's dive in. In this problem, we're given the head of a singly linked list and asked to rotate the list to the right by k places. Essentially, this means shifting the elements in the list so that the last k elements move to the front, while maintaining the order of the other elements. For instance, if the list is 1, 2, 3, 4, 5, and k is 2, we would move the last two elements, 4, 5, to the front, resulting in 4, 5, 1, 2, 3. The input consists of two parts, the head of the linked list, which can be null if the list is empty, and the integer k, which specifies how many positions to rotate. The output will be the new head of the rotated linked list. For example, if we have the input linked list 1, 2, 3, 4, 5, and k is 2, the output will be 4, 5, 1, 2, 3. Here's why. After the first rotation, the last element, 5, moves to the front, resulting in 5, 1, 2, 3, 4. After the second rotation, the new last element, 4, moves to the front, giving us 4, 5, 1, 2, 3. In another example, if the input list is 0, 1, 2, and k is 4, the output will be 2, 0, 1. Since k is larger than the length of the list, we only need to rotate it by k% positions, where n is the length of the list. Here, the list length n is 3, so k%3 gives 1. Rotating the list by one position results in 2, 0, 1. To summarize the second example, we reduced k using the modulo operation, which is key to handling cases where k is larger than the length of the list. After reducing k, we performed a single rotation to get the result 2, 0, 1. Now, consider another example where the linked list is empty, and k is 5. Since the list is empty, there are no elements to rotate, so the output is simply an empty list. These examples highlight the importance of accounting for edge cases, such as when the list is empty or when k is larger than the list length, to ensure the solution works across all scenarios. When solving this problem, there are several edge cases to keep in mind. First, if the linked list is empty, the output must also be an empty list. Second, if k is 0, no rotation is needed, so the original list should be returned. Third, if k is greater than or equal to the list's length, we can reduce k using k%n, where n is the length of the list, as rotating the list by its length results in no change. Finally, if the list contains only one node, rotating it any number of times will yield the same list. The key takeaway is that optimizing the process by reducing k ensures the algorithm handles very large values of k efficiently, avoiding unnecessary rotations and improving performance. To solve the problem of rotating a singly linked list to the right by k places, we can consider multiple approaches depending on the level of optimization needed. The first approach is the brute force method, which involves rotating the list one step at a time, k times. A single rotation is achieved by moving the last node to the front of the list. Specifically, for each rotation, we traverse the list to locate the second-to-last node and the last node. We then update the second-to-last node's next pointer to null and make the last node the new head of the list. While this approach is straightforward, its inefficiency becomes apparent with larger values of k and n, as the time complexity is O, k*n. This inefficiency arises because each rotation requires a full traversal of the list. On the bright side, the space complexity is constant, O(1), since no additional data structures are used. However, given its performance limitations, this method is not ideal for large inputs. A more efficient solution involves using modular arithmetic to optimize the rotation process. The key insight here is that rotating a list of length n by k places is equivalent to rotating it by k%n places, which eliminates unnecessary rotations. Additionally, we can utilize the circular nature of the list to simplify the problem. If k%n is 0, the list remains unchanged, as the rotations bring it back to its original configuration. The process involves first calculating the length of the list, n, and then computing k equals k%n. By connecting the tail of the list to the head, we create a circular structure. From here, the task becomes finding the new tail at position end k1 and the new head at position end k. Finally, we break the circle by setting the new tail's next pointer to null. This approach achieves a time complexity of O, n, because the list is traversed only a few times, and the space complexity remains O, 1. While slightly more complex to implement than the brute force method, this solution is highly efficient and handles cases with large values of k seamlessly. Another possible approach is to use recursion to handle the rotations. The recursive method attempts to simplify the rotation logic by breaking it down step by step. The base case occurs when k becomes 0, at which point the rotations stop. To achieve this, we first compute k equals k%n and then recursively rotate the list by k1 until we reach the base case. Each recursive step involves moving the last node of the list to the front, similar to the brute force approach. However, this method comes with significant drawbacks. The time complexity is O, k*n, in the worst case, as each recursive call involves traversing the list. Additionally, the recursion stack introduces a space complexity of O, k, which can lead to stack overflow for large values of k. While this approach may seem elegant, its inefficiency and potential for errors in edge cases make it impractical for most real-world scenarios. The best choice among the discussed approaches is the optimized solution using modular arithmetic and the circular property of the list. This method stands out due to its linear time complexity and constant space usage. The key insight is that unnecessary rotations can be avoided by reducing k to k%n and treating the list as circular, which allows for efficient computation of the new head and tail positions. While the brute force approach is simpler conceptually, its inefficiency for large inputs makes it unsuitable for scalable solutions. Similarly, the recursive method, although elegant, suffers from high space complexity and the risk of stack overflow. The optimized solution strikes the right balance between efficiency and clarity, making it the most practical choice for solving this problem. By reducing redundant computations and leveraging the list's circular nature, this approach ensures that the rotation is performed effectively, even for very large inputs. In this problem, we are given a singly linked list and a number k, and the goal is to rotate the list to the right by k positions. For example, if we start with the list 1-2-3-4-5 and rotate it by k equals 2, the nodes at the end of the list will wrap around to the front, resulting in 4-5-1-2-3. To solve this efficiently, we need to avoid unnecessary computations and repeated traversals of the list. A naive approach, where we rotate the list one step at a time, would require k full passes over the list, which is inefficient for large values of k. Instead, we aim for an optimal solution by leveraging the properties of the list. The first step in our algorithm is to handle simple base cases. If the list is empty, contains only one node, or if k is 0, no rotation is needed, so we return the list as is. These checks allow us to quickly handle trivial cases without further computation. After handling the base cases, the next step is to calculate the length of the list. As we traverse the list to determine its length, we also keep track of the tail, the last node in the list. For example, in the list 1-2-3-4-5, the length is n equals 5, and the tail is the node with the value 5. Once we know the length of the list, we can optimize the value of k. Rotating the list by its length n or any multiple of n results in the same list, so we can simplify the problem by computing k equals k%n. If this results in k equals 0, it means no rotation is required, and we can return the list immediately. If rotation is still necessary, the next step is to identify the new head and tail of the rotated list. The new head will be the end k, th node, while the new tail will be the node right before it, i.e., the end k1, th node. This requires another traversal of the list to locate these nodes. For instance, if the list length is 5 and k equals 2, the new head is the 4th node, which has the value 4, and the new tail is the 3rd node, which has the value 3. Once we've located the new head and tail, we can perform the rotation. First, we disconnect the rotated section from the rest of the list by setting the next pointer of the new tail to none. This ensures that the list is properly split at the right point. Next, we reconnect the old tail, which we identified earlier, to the original head of the list. This creates the circular connection needed to bring the rotated portion to the front. Finally, we update the head pointer to the new head node, which now marks the beginning of the rotated list. At this point, the rotation is complete, and the head pointer represents the desired output. This entire process takes only 2 passes over the list, one to calculate the length and locate the tail, and another to identify the new head and tail. By carefully managing pointer updates, we ensure the list remains intact and correctly rotated. The result is an efficient solution with minimal overhead, leveraging the structure of the linked list to achieve optimal performance. The time complexity of this algorithm is O(n), where n is the length of the list. The first traversal to calculate the length takes O(n), and the second traversal to locate the new head and tail also takes O(n). Since we perform these operations sequentially, the total time complexity remains O(n). The space complexity is O(1), because we only use a constant amount of extra space to store references like the tail, and new head. Let's walk through an example to solidify our understanding. Suppose the input is head equals 1-2-3-4-5 and k equals 2. First, we calculate the length of the list, which is 5, and identify the tail as the node with value 5. Next, we compute k equals k%n equals 2% 5 equals 2, meaning we need to rotate the list by 2 positions. To find the new head and tail, we determine that the new head is the 4th node, which has the value 4, and the new tail is the 3rd node, which has the value 3. We then update the pointers. The old tail's next points to the original head, forming 5-1, and the new tail's next is set to none, disconnecting 3-4. Finally, the head pointer is updated to the new head, resulting in the rotated list 4-5-1-2-3. This demonstrates the efficiency and correctness of the algorithm. To implement the rotation of a linked list, we start by defining a basic structure for our linked list nodes using the listNode class. Each node has a value and a reference to the next node. Then, in the solution class, we define the rotate_right method. The first thing we do in this method is handle edge cases where the list is empty, has only one node, or if the number of rotations, k, is 0. In any of these cases, we simply return the head as no rotation is needed. Next, we determine the length of the list by traversing it. Starting from the head, we move through the list node by node, incrementing the length counter until we reach the last node. Once we know the length, we make the list circular by connecting the last node's next pointer back to the head. This step is crucial because it allows us to treat the list as a closed loop, which simplifies the process of finding the new head after rotation. After that, we calculate the effective number of rotations needed by taking k modulo the length of the list. This ensures that we don't perform unnecessary rotations when k is larger than the length of the list. We also calculate the number of steps required to reach the new head from the current head, which is given by the difference between the length of the list and the effective k value. Using the steps calculated earlier, we locate the new tail of the list. Starting from the current head, we move through the list one node at a time for the number of steps required to position the new tail. Once we reach this node, the new head will be the node immediately following it. At this point, we break the circular connection by setting the new tail's next pointer to none. This effectively separates the rotated portion of the list from the rest, restoring it to a standard linear structure. Finally, we return the new head, which is now the starting point of the rotated list. Here, we begin by defining the listNode class, which represents a node in our singly linked list. Each node contains an integer value, val, and a reference to the next node, next. We also provide a constructor to initialize the value of the node. Moving into the solution, the rotate_right method takes 2 parameters, the head of the linked list and an integer k, which represents the number of positions to rotate the list to the right. First, we handle simple base cases. If the list is empty, contains only one node, or if no rotations are needed, we simply return the head as is since no changes are required. Next, we calculate the length of the list. Starting with a length of 1, we traverse the list using a current pointer, incrementing the length until we reach the end of the list. At this point, we have determined the total number of nodes in the list, which will be useful for subsequent steps. Now that we know the length of the list, we proceed to make the list circular by connecting the next pointer of the last node back to the head. This helps us efficiently handle the rotation. Next, we handle cases where k is greater than or equal to the length of the list by taking the modulus of k with the length. This ensures that we only perform the necessary rotations. To find the new head position, we calculate the number of steps required to reach the new head from the original head by subtracting k from the length. We then traverse the list again to identify the new tail node, which is located just before the new head. Once the new tail is identified, we break the circular connection by setting its next pointer to null, effectively making the list linear again. Finally, we return the new head, which represents the rotated list. To solve the problem of rotating a linked list, the first step is to determine the length of the list. We start by initializing length to 1 and setting current to the head, which is the node with the value 1. From there, we traverse the list node by node, incrementing the length each time we move to the next node. For instance, moving to node 2 sets the length to 2, then to node 3 makes it 3, and so on. By the time we reach node 5, the length becomes 5, and current is at the tail of the list, which is also node 5. Once we have the length, the second step is to make the list circular by connecting this tail node back to the head. This creates a circular structure where the list cycles back to the beginning after node 5, forming 1, 2, 3, 4, 5, 1. Now that the list is circular, the next step is to find the new head position after rotation. To do this, we first compute k modulo the length, which ensures the rotation count is within the bounds of the list. For k equals 2 and length equals 5, we get k equals 2. Then, we calculate how many steps to walk from the current head to locate the new head. The formula is steps underscore to underscore new underscore head equals length k, which gives us 5, 2 equals 3. To find the new tail, we walk steps underscore to underscore new underscore head 1 steps from the current head. Starting at node 1, we move to node 2, then to node 3. This makes node 3 the new tail, and the node immediately after it, which is node 4, becomes the new head. Finally, we break the circular connection by setting new underscore tail dot next to none. The resulting list is 4, 5, 1, 2, 3, which matches the output 4, 5, 1, 2, 3. In the second example, we rotate the list 0, 1, 2 by k equals 4. First, we determine the length of the list by traversing it. Starting at the head with the value 0, we move to node 1, then to node 2, resulting in a length of 3. The current pointer is now at the tail, which is node 2. Next, we make the list circular by connecting the tail back to the head, forming the cycle 0, 1, 2, 0. To find the new head position, we compute k equals k% length equals 4% 3 equals 1. This simplifies the rotation to just one step. Using the formula steps underscore to underscore new underscore head equals length k, we get 3, 1 equals 2. To determine the new tail, we walk steps underscore to underscore new underscore head 1 is equal to 2, 1 equals 1 step from the current head. Starting at node 0, we move to node 1. This makes node 1 the new tail, and the node after it, which is node 2, becomes the new head. Once we have identified the new tail and new head for this example, the final step is to break the circular connection. We set new underscore tail dot next to none, which disconnects node 1 from node 2. The resulting list becomes 2, 0, 1, and the output for this rotation is 2, 0, 1. Moving on to the third example, we rotate the list 1, 2 by k equals 3. Again, the first step is to determine the length of the list. Starting at the head with the value 1, we move to node 2, resulting in a length of 2. At this point, the current pointer is at the tail, which is node 2. Next, we make the list circular by connecting the tail back to the head, creating the cycle 1, 2, 1. For the third example, we now calculate the new head position. With k equals 3 and length equals 2, we compute k equals k% length equals 3% 2 equals 1. Using the formula steps underscore to underscore new underscore head equals length k, we get 2 1 equals 1. To locate the new tail, we walk steps underscore to underscore new underscore head 1 is equal to 1 1 equals 0 steps from the current head, so the new underscore tail remains as node 1. The node after the new tail, which is node 2, becomes the new head. Finally, we break the circular connection by setting new underscore tail dot next to none, resulting in the list 2 1. The output for this rotation is 2 1. To analyze the time complexity of the algorithm, let's break it down step by step. First, we determine the length of the linked list. This involves traversing the entire list once to count the number of nodes. Since we visit each node exactly once, this step takes n time, where n is the total number of nodes. Next, we make the list circular by connecting the tail back to the head. This is a simple pointer adjustment that only requires constant time, or 1. After that, we calculate the new head position. Using the modulo operation, we compute the effective number of rotations as k modulo the length of the list, which is a constant time arithmetic operation. We then determine the number of steps to the new head as length minus k, another 1 operation. These steps together lay the groundwork for efficiently rotating the list. At this point, we need to break the circular list to finalize the rotation. To do so, we locate the new tail by traversing the list up to a specific position, which is determined by the number of steps to the new head minus 1. In the worst case, this involves traversing the entire list if k is 0 or a multiple of the list length, resulting in n time. When we sum up the time complexities of all steps, n, for determining the length, 1, for making the list circular, 1, for calculating the new head position, and n, for breaking the circular list, we get a total time complexity of n. Now, for space complexity, the algorithm operates directly on the input list without using any additional data structures. We only use a constant amount of extra space for variables like pointers and counters, which means the space complexity is 1. Let's now compare this optimized approach to a brute force solution. In a naive method, we would rotate the list one step at a time, repeating this operation k times. For each rotation, we would traverse the entire list to update the head and tail pointers, resulting in a time complexity of k*n. This becomes highly inefficient when k is large. In contrast, the optimized algorithm reduces the time complexity to n by avoiding redundant rotations and leveraging the modulo operation to calculate the effective number of rotations. Importantly, the space complexity remains constant, or 1, in both approaches. When we analyze the best, average, and worst cases, we see that in the best case, where k equals 0, no rotations are needed, and the algorithm completes in 1 time. For an arbitrary k less than n, the operations are proportional to the size of the list, leading to an average case complexity of n. Even in the worst case, where k is very large, the modulo operation ensures that the number of rotations is reduced to a manageable value, maintaining the overall time complexity at n. Finally, let's solidify our understanding with a mathematical proof for the algorithm's big O complexity. The dominant factor in the time complexity comes from traversing the list twice, once to compute its length and once to locate the new tail. Each of these operations requires n time, as they involve visiting each node once. All other operations, such as making the list circular, performing modulo calculations, and breaking the circular connection, are constant time operations or linear in the size of the list. Therefore, when combining these steps, the overall time complexity remains n. This ensures that the algorithm is efficient for handling linked list rotations, regardless of the size of the input. When solving the rotate list problem, there are a few common mistakes to watch out for. First, many people overlook the importance of reducing k modulo the length of the list. Without this step, if k is larger than the list length, you end up performing unnecessary rotations, which wastes time and computational resources. By calculating k%n, you ensure that you only rotate the list the necessary amount. Next, handling edge cases is crucial. Special conditions like an empty list, a single node list, or when k is 0 often lead to runtime errors or incorrect results if not addressed properly. For these scenarios, you can simply return the original list without any changes. Another frequent mistake is in modifying the list structure itself. If you break or rearrange pointers incorrectly, the linked list can become corrupted, which makes debugging difficult. To avoid this, take extra care when reconnecting the tail to the new head, and visualize the pointer manipulations to ensure everything is aligned properly. Another area where mistakes commonly occur is in the approach to solving the problem. Using a brute force method, where you rotate the list one step at a time, might seem straightforward, but it leads to a highly inefficient O(n*k) solution. This becomes impractical for larger values of k or longer lists. Instead, an optimized O(n) algorithm that uses modular arithmetic and the two-pointer technique is much more efficient. Similarly, incorrect length calculation is another pitfall. If you miscount the length of the list during traversal, the subsequent modulo operation will be incorrect, and this will result in an inaccurate rotation. To avoid this, always traverse the entire list once to calculate its exact length before proceeding with the rotation logic. Beyond solving the problem, this challenge is often designed to test several key skills in interviews. First, it highlights your ability to recognize patterns, such as the use of modular arithmetic in circular data structures. This insight can simplify many problems involving cyclic operations. Additionally, interviewers frequently test your attention to detail through edge cases, such as when k is 0 or the list is empty. Addressing these cases explicitly shows that you've considered all possible scenarios. Optimization is another critical focus. While a brute force solution might be acceptable as an initial step, interviewers typically expect you to refine your approach to achieve O(n) complexity. Clearly explaining how you transition from the brute force method to a more efficient solution demonstrates your problem-solving process. Finally, this problem is an excellent test of your ability to manipulate pointers in a singly linked list. You should be prepared to discuss how you maintain the integrity of the list while modifying its structure and why your approach avoids common pitfalls. This problem also shares similarities with several other linked list problems, making it a valuable learning experience. For example, LeetCode 19, remove nth node from end of list, involves using the two-pointer technique to locate nodes efficiently. LeetCode 876, middle of the linked list, focuses on traversing the list to find specific nodes, which is another foundational skill. In LeetCode 143, reorder list, you'll encounter pointer manipulation to rearrange nodes, much like in rotate list. Lastly, LeetCode 206, reverse linked list, tests your understanding of basic linked list operations and pointer updates. Practicing these related problems will deepen your understanding of linked list manipulation and help you recognize patterns across different questions. Now, let's explore some alternative approaches to solving the rotate list problem. One efficient method is the two-pointer technique. In this approach, you use two pointers to locate the new tail and the new head in a single traversal. Specifically, the new tail is at position end k1, and the new head is at end k. This method is highly efficient, running in O(n), but requires careful pointer management to ensure correctness. Another approach involves converting the list into a cyclic structure by connecting the tail to the head. Once the list is circular, you can break the cycle at the appropriate position to complete the rotation. This method is intuitive and visually easy to understand, but you must remember to disconnect the cycle to restore the list to its proper form. Finally, there's the array conversion method, where you convert the linked list into an array, perform the rotation, and then convert it back into a list. While this approach is simpler to implement, it uses O(n) additional space, making it less efficient for large lists. Each of these methods has its trade-offs, so it's important to choose the one that best fits the constraints and requirements of the problem. Great job following along. To wrap up, we summarized the solution, highlighted key concepts like linked list manipulation and modular arithmetic, and reflected on the importance of edge cases and problem solving. Keep practicing and growing your skills. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!